All right. This is our region that we're trying to find the integral of. For that problem that we're doing, they gave us the conversions, the change of variables that they wanted us to use. What we're going to be doing is doing this. Basically, this is converting x and y, a function x and y. If you were to do it in x and y, you'd have to, this notation means dA means little chunks of area. That means you got to break it down to two variables, x and dx dy or dy dx, and the region in the xy plane. And you could do this one that way. It's not completely unreasonable, but this whole chapter is about learning how to do transformation of variables. And when you do that, you're going to transform the region R to you're going to use whatever variable you want, but if it's a generic one, they tend to use u and v. So we'll be converting everything in x and y to u and v's via the equations they gave you or equations you have to come up with on your own. The region has to be converted to a region in the UV plane. That's S. This is R, and then we'll be drawing S when we get to it, which will be the region in the UV plane. Your function, same function, but it's going to rewrite it in terms of u and v. So that's the same function f, but you're going to replace x with its equation in u and v. You're going to replace y with its equation in u and v. And then you have to remember, it's just not that. You need what's called the Jacobian, because when you basically transform this region to S, sometimes it tweaks it. And this area is not the same as that, because when you bend it, it distorts it, and that's accounting for the distortion. To do that, and the book that I was looking at used JUV, called the Jacobian, but it's a determinant of partial derivatives. You're going to see this notation a lot, which is why I made you do it last night. There's called a Wronskian for, basically you're going to see this in a matrix, either 2 by 2 or when you get to 3 variables, 3 by 3, and it's a determinant of a bunch of partial variables, all the different combinations when you're doing transformations. And you're going to see this in all your levels of math you're taking now. Math 3, Math 4, Math 6. They all involve something similar. So get used to it. All right. I'm going to work at this out the usual way. So if you were just going to not bother with the change variables, you would need to know the curves, the upper curve and the lower curve. I'm going to draw it bigger. And I'm going to remind you. Basically, we have a bunch of bounding curves. That's this side right here, and I'm going to focus on that. You need to get the equation of it, depending what you're going to choose to do it in. Probably y is equal to, maybe I'll have to rearrange it afterwards, but how do you find the equation between 2 points? This is 1, negative 1, and this is 2, comma 0. Well, I mean, most people at this point are just going to count slope and know where it's going to intersect, but if not, you got to do your slope formula. 0 minus negative 1 over 2 minus 1. I don't have time to go through it in detail, but your slope is 1. It's going 1 up and 1 over. 45-degree angle. Those are slopes 1. Those are slopes negative 1. Note that. Then I would plug it in y minus. I'll use this. No, it doesn't matter. Yeah, I'll use that. Y minus 0 is equal to my slope times x minus 2. Y is equal to x minus 2. Slope is 1, and if you continued it down, it would intersect at negative 2, so it would hit there. But anyway, I'm going to clean this up, so make sure you review the linear stuff. It comes up a lot on these. I'm going to note that this is y is equal to x minus 2. And similarly, you have 4 bounding curves, and you need to know all of them if you're going to work in the xy plane. You actually will, it's useful to know them in general. So I'm just going to draw them all out. Here's your region. I'm going to erase that. But that one is y is equal to x minus 2. This one is y is... y is equal to x minus 2. This one is y is equal to negative x plus 0, essentially. This one is y is equal to negative x plus 2. And this one over here is y is equal to x plus 0. Okay, and yeah, we can work with that. So let me set up the integral and work it out. The idea now is you have to note that you're doing upper curve minus lower curve, doing slices this way. My upper curve is a y is equal to x. My lower curve will be the y is equal to negative x. For this side, but once I get to this cutoff, my upper curve and lower curve changes. Now my upper curve is y is equal to negative x plus 2, my lower curve is down here. So if I'm going to do it this way, I need to separate into two separate regions and do two separate integrals, region 1 and region 2. And I'm going to do it this way. It's not that bad. It's going to look tedious. I mean, well, I'm not going to lie, it is tedious. I'll do it slices this way going along the y, so we're going to do dy first, y is equal to y is equal to, dx afterwards. Okay, I'm doing the R1 first, doing this side. So my upper curve is x, y is equal to x, my lower curve is negative x. And then that means I'm doing all these, I'm doing region 1, upper curve to lower curve, right here. And then I'm doing all the slices from there all the way to the edge of that particular half of the overall region. So that's from 0 to 1. X equals 0, x equals 1. And then my integrand doesn't change because I'm keeping it rectangular. That's the first piece. Then I'm going to do region 2 over here. X, y is my integrand. I'm doing it with respect to y first and x, so I can do the same thing. Slice it this way, and then, so it's upper curve to lower curve. This one is y is equal to x minus 2 is my lower. Y is equal to negative x plus 2 is my upper. And I'm doing all those slices from 1 to 2. Okay, I'm going to erase this because I don't need it anymore. My picture's over here, but that's the details that I would need. I'm going to need those equations, by the way, but I'll remember. And let me just start working this out. Let's see. Well, I'm going to rewrite it over here. No, I'm going to throw in those details. Because I got to know which way, what's being treated as a constant, what's being treated as a variable for each layer of integration. Got these Amazon pens in bulk. They're not bad, but they're not great. All right. With respect to y first, y is your variable, x is your constant. I don't have time to go into the details. You better get that down. I'm going to bump up the power of y by 1. I'm carrying over that x. That's my antiderivative of y, and x is a constant I'm bringing down. And I'm plugging in for y, x and negative x. Then I got to do another layer of integration. All right, it's going to be 1/2 x cubed minus 1/2, and I'm going to plug that in. It's going to get squared. So it'll be x squared, it'll be x cubed. Is that right? I think it's 0. Let me see. Yeah, I feel like it's 0. I'll double check it afterwards, and if it's wrong and I spot my mistake, I'll just delete this whole video and you'll never know. I feel like it's 0, but that's only the left half. Respect to y. No. Okay, let me see if the other piece gives me something. This one was y is equal to negative x plus 2, and this lower bound was y is equal to x minus 2. And this one was from x equals 1 to x equals 2. All right, let's see. Same integrand, same order of integration, different bounds, but I'm doing it with respect to y first. So it's going to be the same thing. I'm going to bump up the power. I'm going to do the power on the y, because that's your variable of integration. X is a constant that comes down. going in there, so that's your constant, and then I'll plug in upper bound in place of y squared minus lower bound, oops, it's a plus, squared, and that'll be my antiderivative, or that's my integration of the first layer, and then it'll be a function in x, and then I've got to do 1 to 2 with respect to x. Let me FOIL this out. It's going to be, it's going to cancel. X squared is going to cancel. I'm doing a lot of it in my head. The 4's are going to cancel. The middle terms will not cancel. I'll get a negative 4x there. Oh, it will. Oh, it's going to cancel. I get 0 again. I'm going to check this. No, that is correct. That's 0 for that piece, that's 0 for that piece. I feel like that might be a terrible example to use, but that's the example the book gave. Okay, regardless of that, that's how you would set it up. Your integral can come out to 0, that's just another number. I just thought there'd be more to it. It still can be used to illustrate it, and I'm not going to do another one. I've had you work through a lot of the pieces here. It's nice and convenient, it just has a weird answer that's very unsatisfactory, but it's still going to work. I'm still going to use this example to do the transformation, because it'll still illustrate the concepts that you have to do. And you'll get the same answer, even if it weren't 0. Okay. So for this problem that I sent you, that you worked on all the pieces last night, they gave you the U and V transformation they want you to use. And the one that Bachelor gave you also gave you the conversions that he wanted you to use. But I recall him, once you get the hang of it, he will move on to situations where you do not have, they don't give you the U and V, and you have to come up with it on your own. So I'm going to talk about that. Okay. So to come up with your own U and V, I had you convert the vertices from x and y to u and v. Your vertices were 0, 0, and you converted that to u, that's x and y. What's another one? 1, 1, 2, 0, and 1, negative 1 were your vertices. Okay, another thing, and if you're going to come up with your own, it often helps you to look at not the vertices of a polygonal region, but to look at the bounding curves that I was looking at earlier. So let me blow it up one more time. Label them. And the way I had it was in slope-intercept form, so that I had the y equals by itself for purposes of setting up those bounds of integration. This one was, what was it? Y is equal to negative x plus 2. This one was y is equal to x minus 2. This one was y is equal to negative x. And this one was y is equal to x. Okay, that's slope-intercept form, y is equal to mx plus b, all 4 of them. What you want to do is you want to actually rearrange it into standard form for linear boundaries, linear curves. Standard form, despite the name, is not that common, but in some contexts you like to see it like that, where you move the x and y together and just have a constant on the other side. We do that with planes and other quadratics sometimes. But anyway, we don't often see it done with lines, but yeah, we're going to see it here. So this one I got to get the y and x on one side. Move it all to one side. 1x plus 1y is equal to 0. That's standard form. Same thing here. I'm going to move it over. I'm going to move it over to that a slightly different way. Let me see. What was it? Y is equal to negative x. No, y is equal to x. I'm going to move the y over to the other side. So I'm going to subtract y from both sides, and that gives me a 0. For no particular reason. I'm going to just want a positive x, and I'm also kind of matching it up with what we're going to be doing. Okay. This one I'm going to get x plus y is equal to 2. And this one I'm going to do the same thing. I'm going to get x as my positive lead coefficient, subtract the y, move the 2 over the other side, and then just rewrite it that way. So those are all the equivalent forms where I put in standard form. X plus y is equal to 0, x plus y is equal to 2. This one I could have wrote in different ways. I could have done y minus x, but I chose to go with the other way. X minus y is equal to 0. And I want it to be consistent here. X minus y is equal to 2. So I'm anticipating what I want to happen. So I'm going to clean this up by erasing the slope-intercept forms, which are not going to be helpful for these purposes. Those are my 4 equations of the lines that make up this region in standard form. So I gathered up all my x's, y's together. And now I'm going to choose my u and v. And I'm setting u to be some expression involving x and some expression involving v. And ideally, what I would like to have is transforming it to a region where I can have nice clean boundaries. Maybe just constants like 0 and 1 and v is equal to 1 and 2, something like that, where it's going to be super easy to integrate. I want it to be putting in functions and doing all kinds of things with it. And the goal, and that would mean I'd be looking to try to transform it into a region that is rectangular. So these are all just horizontal and vertical lines. There are no weird curves or even diagonal lines. They'll just be u is equal to 0 and 1, v is equal to 1 and 2, something like that. That's not accurate, but that's the idea. So the way I can do that is note that I have the same combinations of x and y. I have x plus y on this lower left one, and I have the same one here. It's just that this is equal to 0 and that's equal to 2. And you know what? I'm going to set that to be something. Let me go check how they did it, because the idea is I have options. This is actually, so I'm not going to do the same thing the way the book does it. I'm going to let that be u. So I'm going to let u be equal to x plus y, which means that edge of it, when I transform it, this edge which is y is equal to negative x, will transform to just a line u is equal to 0 in my uv plane. That'll transform to u is equal to 2 in the uv plane. The other edge, and that edge have the same expression as well. When they're parallel lines, it's going to be like that. I'm going to set it to be v. V is equal to x minus y, so that would be v is equal to 0 and v is equal to 2. I have many options to do it, so this is just the way I've chosen to do it. I could have made that u and that v. I could have rearranged it to y minus x, and back when I was making that decision. But those are the transformations that I'm doing, which is different from what the book did. Again, the book just assigned it to us. We are going to, and they gave us it in terms of x and y. They gave us x is equal, they gave the equation in terms of x expressed as u and v, y is that, and then I had you work this out to get it in terms of u is equal to an expression in x, v is an expression in y. They're interchangeable. Here I've actually set u, I've already got my equations in u in terms of x and y, and I've got to go, so I have this version of it, and I got to go backwards doing the same system of equations, elimination, to get this specifically to do those. Okay, but anyway, I'm off track from the book. I'm on my own thing. That's what I'm going to do. Alright. Anyway, this is just to illustrate how I chose my u and v. Again, getting these lines in this form to see the same combination x and y's in different places and setting u to be one of those combinations. So it's u is equal to a clean constant, and then v to the other one, so v is equal to a constant. But now, I'm going to erase everything except for those. That was completely made up. This was me breaking it down for you. But now I've chosen my change of variables, which is different from what the book is going to do. But I'm fine, we can still do it. I'm going to let u equal to x plus y, and v is equal to x minus y. Okay, I'm going to do some quick elimination and rewrite it. I'm going to do it here, get the results, but then erase. So I'm just rewriting it in a different form. I'm not even sure I need it, but I'm going to get it anyway. I'm going to eliminate the y. I'm going to get u plus v is equal to 2x. X is equal to u plus v over 2. I'm going to take those same equations and I'm going to multiply the v1 by negative 1. Wait, what happened? So, to eliminate x, and so y will equal u minus v over 2. I'm not 100% I actually need that, but I got them if I do. So I'm just organizing so I have my pieces ready to go. But I haven't done this in a while, so I actually don't know how it's going to pan out. I know it's going to work, I just don't know what I'm going to need to get there. Okay. I'm ready to start transforming it. I can transform the vertices now. Or I can transform the curves. Well, I'll do it 2 ways. So what I had you do last night was transform your vertices. And again, it's going to be different because I'm doing different things. Okay, but anyway, my u is x plus y, 0 plus 0. My v is x minus y. So 0, 0 transform to 0, 0. 1, 1. I'm going to get 2, comma, 0. This one I'm going to get what am I doing? 2 plus 0, 2 minus 0, 2 comma 2. And this one is 0 comma 2. Okay, so again, different from what you did last night, but it's the same thing, convert my vertices. Let me draw my UV plane. This is important because I'm going to be integrating with respect to u and v. And I've got to set up new bounds based on the region here in the UV plane. Okay, but anyway, my new region is going to have vertices at 0, 0, 2, 0, 2, 2, and 0, 2. Okay, so my choice of variables reoriented it and stretched it a little bit because now it's got lengths of 2. Okay. So that's my new region. That's S in the formula there. That's an S, by the way. Okay, I could have done it differently by looking at the curves here. I did the exact thing where I erased it, but let me put it back up. This was, oh shit, I forgot it now. This is y is equal to x minus 2, so that's x minus y is equal to 2. That's x minus y is equal to 0. This one is x plus y is equal to 2. And this one was x plus y is equal to 0. Okay, so those are the bounding curves written in standard form so that I can make a clean u is equal to x plus y. So my bounding curves, maybe I shouldn't even put it on there. This one becomes v is equal to 0. This one becomes v is equal to 2. This one becomes u is equal to 0. And this one becomes u is equal to 2, like I did earlier. So now I can draw my region not by looking at vertices, I can look at by looking at bounding curves. So those 4 sides transforms to these equations. U is equal to 0, u is equal to 2, v is equal to 0, v is equal to 2. It's the same region. But anyway, that's another way to look at it. But that was good for us deciding on what to make u and v if we were completely left on our own to figure out what transformation to use. Which again, Bachelor has done that in the past. I've seen him do it. Usually later after you get familiar with this. It's my region. I'm ready to go. I'm going to do this. Oh, no, I'm not ready. Jacobian. Let's do the Jacobian. I won't need that. I'm going to transform. I did my R to S. That's pretty easy. I just got to replace X and Y in my integrand with these 2 expressions. The Jacobian takes some work, so let me do that. Jacobian of u and v. And then in here is the absolute value, so I mentioned that. You can do the fishy thing, but then you take the absolute value. Let's see. dx du, dx dv, dy du, dy dv. What you need is equations that have x is equal to, I put this in your text a bunch of times, x equals something with u and v only. Y is equal to something with u and v only, so that you can take the derivative of x with respect to u, derivative of x with respect to v, derivative of y with respect to u, derivative of y with respect to v, because that's what you need. So you got to look on your paper to find that type of equation. Is it there? Is it there? Where is it? Right here. X equals y is equal to in terms of u and v. Organize your things, please, so I don't have to spend multiple attempts to get you to find that equation, and then you lose it, and I gotta ask you to find it again. There it is. dx du is 1/2. dx dv is also 1/2. dy du is 1/2. dy dv is -1/2. With linear, they're just coefficients oftentimes, although they could be functions of u and v. That's why this Jacobian is technically a function of u and v. It so happens with linear things, it'll turn out to be a constant. Ready for the fishy thing? -1/4 minus 1/4 is equal to -2/4, which is -1/2. That's my Jacobian. I will be taking the absolute value of it, so in my integral I have to throw in an extra factor of 1/2. I'm ready to go. Now I'm definitely ready to go. S, I'll put my bounds up now. I mean, I still sort of have to decide whether I'm going to integrate with respect to u or v first. It's not a weird region where that would matter. It's a fairly straightforward one, so I'll just go with v first, because that's like y, so I'm going to slice it this way. Then I'll do all my slices that way. V is equal to 0 to 2. Very clean limits of integration now. That's why this transformation that I did is going to help me so much. U goes from 0 to u goes to 2. And it doesn't matter, the other way would be just as easy. X times y. I need to rewrite that in terms of u and v, right here. X times y. Okay, actually the integrand's uglier, but the region is easy. I'm going to erase that because I need space for my Jacobian. -1/2 absolute values. There's an extra factor there. That is your Jacobian. dv du. Okay, that's going to be absolute values. So the negative's going to be gone. 1/2. That's another half. That's another half. 1/8 out here. And then I'd be foiling out u plus v times u minus v. Okay, and that's my integrand in u, and I just do that, and that's my answer. That's literally the same thing as if I'd done an x and y. Alright, if that answer was 5, I'll get 5 here if I did it correctly. If the answer was 0 there, I'll get 0 here. If the answer was 0 there, I should get 0. But let's see. Power rule on your v. Think about it. I'm going to pause for 20 seconds. Not 20 seconds. Okay, that's a constant. Antiderivative, we're doing with respect to v. U squared is a constant. I got to add that variable. That's like a 3. Antiderivative of 3 is 3x. This one I got to do a power rule. And I'm plugging in 0 and 2 for v. That's at 1/8, and then I'll have to do an integration with respect to u. Plug in for v. U squared minus 8/3. That's just a 2 plugged in. Then I'm going to plug in the 0. Minus 0, fortunately. And then I got to integrate with respect to u. You've done this before, so I'm not spending much time doing it. 2u squared minus 8/3. And I have to integrate. That's the inner integration done. I got to do the u. Power rule on that. 2/3 u cubed minus 8/3 u. 0 to 2 with a 1/8 out there. 2 plugged in is going to be 16/3 minus 16/3 and then minus 0, 0. It comes out to 0. I don't have time to go to the arithmetic, but anyway, that's how you do it. Convert your region. based on either the u and the equations that they give you, and be able to work with them and go from the u and v in terms of x and y to the x and y in terms of u and v. I did need that because I had to replace my x and y, my integram, with that form. I didn't need this form, did I? I needed to convert things over here. I don't know. I think they're both useful. I've never done it where I just omitted one. I needed both of them, I believe, for various things. There it is. Go ahead and take care of that other problem with a bunch of a's and 3a and whatnot, but same idea. I would try to find a problem that has actual numbers rather than that one with the 3a and that triangle one that you sent me. That's a little bit more abstract because you'll have constants to deal with that are constants the whole way through that come on your answer. Your answer may have like a 8a over 3 or something. I don't think you want to deal with that on your first try at this technique. All right, best of luck to you.